In the last two videos, we have just gone through the optimizers and loss functions in the compile functions and how we should select the optimizers and loss functions for different deep learning problems. In this video, I will provide you more details about the last argument in the compile functions, that is the matrix. Let's go ahead and get started. Just a very quick recap. The metrics are not involved in the entire training, that is not involved in the forward propagations and also the backward propagations. And metrics is just an additional evaluation function that is used to judge the performance of the models. However, this is very important because it's difficult to judge the performance sometimes based on the loss value, such as the mean squared error, root mean squared error. Therefore, sometimes an extra metrics such as accuracy and also the MAE are used for additional evaluation. Let's take a look on the details. To compile a functions, a loss functions and an optimizer are needed to be specified. However, metrics are optional, but however, they can be used to specify to judge the performance of a models. Metric functions are very similar to the loss functions, except that the results from evaluating a matrix are not used when training the model. There are 6 main categories of the matrix: accuracy metrics, probabilistic metrics, regressions metrics, classification metrics based on true, false, positive, and negatives, image segmentation metrics, and hinge metrics for maximum margins classifications, mainly used for SVM. And let's go through the examples one by one. The first metric is the accuracy. Accuracy calculates how often predictions equals to labels. Remember, these predictions has to be exactly equals to the labels. This matrix creates 2 local variables that includes the total and also the count, and that we use to compute the frequency when that which y predicts match the y true. Let's take a look on the example here. Here, we just define the y true value is the 0, 0, 1, 1, 1, and then the y predictions is 0, 0.2, 0.4, 0.95, and 1. In that case, there are 2 values that are matched with each other. And we can use the TensorFlow matrix dot accuracy to give the predictions to calculate these metrics. So we first, of course, we assign this matrix equals to the dot accuracy functions. And then we just use the dot update status and provide the y true and y predicts 2 arguments into these dot update functions. And it will help us to calculate the result. Because 2 out of 5 are predicted correctly, so we have around 40% accuracy. Now let's take a look on the other metrics, binary accuracy. Binary accuracy calculates how often predictions match binary labels, and these metrics creates 2 local variables, again, total and count, that are used to compute the frequency with which y predicts match the y true. Again, we have 2 NDOA that is exactly the same as the previous example. However, for this time, we change it to binary accuracy, and then we use this to update the state. Let's take a look on this. For binary accuracy, we use the threshold to see whether it is equals to 1 or it is equals to 0. Say, for example, for the y true, we just keep it as the 0, 0, 1, 1, 1. For the y predicts here, if the y predicts is larger than 0.5, we will just one off this to 1 and set the values to 1. And then if the y predicts is less than 0.5, we will set it to 0. In that case, we have 0, 0, 0, 1, 1. And therefore, because 4 out of 5 are predicted correctly, so we have an accuracy up to 80% here. This is just the default value. Of course, you can change this to another values that another value for the threshold that you want. But for this example, the y-predict will become, just like what I mentioned, 0, 0, 0, 1, 1. Therefore, it will have 80% accuracy here. For another accuracy matrix, that is the categorical accuracy, it calculates how often predictions match one's hot labels. This matrix again calculates two local variables, that is the total and count, that are used to compute the frequency with which y-predict matches with the y-true. Here we have two NDOA, and the first NDOA is just say one's hot labels, and then the second array is the wide predictions. Now we are using the categorical accuracy, so we just change the matrix to this one, and then we update the state, and then we run it off and get the accuracy. These metric calculations involves two steps, and the first step is that at which we need to find an index at which the maximum values occurring that will be identified with the use of argument max. So we are going to use these argument max functions to identify the maximum value. And then if it is same for both y-predict and also y-true, it's considered accuracy. The logic is like this. Now, first of all, we use the argument max functions to get the maximum values positions for the y-true. That is 4, 3, 2, 1, 0, because this is a one-hot enabling, so we expect that is a sequential numbers. And then for the argument max for the y-predict, you will get say 3, 3, 2, 1, 0. In that case, because this is the 0, 1, 2, 3, and you got the maximum value positions 3, 3, 2, 1, and then 0. Now we just compare these two maximum positions to see whether whether the y-predictors are predicted accurately. Now, if I run this out, you will get the same results, that is 80%. So we just sum up the count that the y-true is equals to y-predict in terms of their positions, and then we just divide it by the length of the y-predict and then times 100% to get the accuracy. The other one is the sparse categorical accuracy. It calculates how often predicts match integer labels. Therefore, instead of the one-hot label, we would like to see if whether the predictions match the integer label. And again, this matrix creates two local variables, total and count, and that are used to compute the frequency with which y-predict matches the y-true. But for these times, the y-true is not a one-hot encode, it's just like an integer label. Now, if I run this out, we have a 75% accuracy here. Again, the calculations involve two steps. The first step is to get an index at which the maximum values and in y-predict occurs will be identified, and then with the use of argument max functions. And then if the index is same as the y-true, and is considered accurate. So now we just get the y-predict maximum position. Let's take a look on that. That is 0, 3, 2, 3. Because we need to calculate the count of which predicted correctly, and so we just flatten the true here. So it gives us a 0, 1, 2, 3. Now we try to compare to see which values are predicted correctly in terms of their positions. And you can see 0 is predicted correctly, 2 is predicted correctly, 3 is predicted correctly. As a result, it gives us 75% of accuracy. Another commonly used accuracy metrics is a top K categorical accuracy. So top K categorical accuracy calculate how often one hot target are in the top K predictions. Y predicts is firstly ranked in the descending order of the probabilities values. And if Y predicts present in the index of the non-zero Y true is less than or equals to K, is considered accuracy. In that case, this top K is actually a threshold to determine how accurate the predictions is. Say, for example, we have a Y true ND array, and we have these Y predicts ND array. Let's run this cell first. Now, if I set the top K equals to 1, equals to 2, or equals to 3, it will give me different results. The first is 40%, and then 80%, and then the last one is 100%. Let's take a look on the logics behind. First of all, we want to rank the prediction. Let's get back to the original matrix here. So we have the 1, 0, 0, 0, 0. Therefore, we have 1, 4, 4, 4, 4. Because this is the highest probabilistic values. And so in that case, that gives us a rank number 1. And then because the remainings are equals to each other, so they will be equals to 4. 1, 4, 4, 4, 4, and 1, 4, 4, 4, 4 for the second row. And then for this one, this is the highest one, and then this is the second highest. So 1, 2, here you can see 1, 2, and then 4, 4, 5. That is the 1, 2, and then this is the 4, 4, 5. And then again for this one, for the fourth row, that is 1 and then 2. Yep, that is 1 and 2, and then 4, 4, 4. Similarly, it will give us the rank for the final row. And then now we would like to identify the index of non-zero Y true. Now let's take a look on that. Now we want to identify the rank according to the index of non-zero Y true. In that case, for this one, so 4, 4, 4, 1, 4. And then because the last value is true, and it should return me the 4 in the first value for the first value. And then for this one, this is false, 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 true, false. In that case, for this one, it should return me the 1. Now let's take a look on the calculations. The first one is 4, correct? And then the second one is 1, correct? And then the third is the 2, correct? And then so and so. We got the 1 and 3 here. Now we are ready to assign a K value as the first whole. And then once we have that first whole, we count how many rank are higher than that K value and calculates the accuracy. Say, for example, for this one, we use the K top values equals to 1. In that case, 2 of them is higher than or equals to 1. As a result, 2 out of 5 are predicted correctly, and therefore we have 40% accuracy. And then for 2, that is 1, 2, 2. So we have 3 out of the 5, and then we got 60%. And then for the K top equals to 3, we have 4 predicted correctly out of 5. So we have 80% here. Again, if the targets are not integers, are not one-hot labels, and instead of one-hot labels, we have the targets is an integer target, then in that case, we would like to apply for the sparse top K categorical accuracy. Everything is very similar, but instead, just the Y true value here is not the one-hot label. Now again, if I run this out to get the Y true and Y predict, and if I assign different threshold, and we will get different accuracy in terms of the percentage. Let's see the logics behind. First of all, we want to rank the prediction. Now let's take a look on the predictions here. This is the predictions. We got the 1 and then all the rest are 0. So we have the rank like the 1, 3, 3, 3. And then for the second row, because this is 0.8, so we have this is the number 1 rank. And then for these two, they are equals to each other. So we have 1, 3, 3, 4 here for this one. And then for this one, this is just like the 1, 2, 3, 4. So that should be 1, 2, 3, 4. Yep. 0.6. Yep, that is correct. And then we would like to identify the index of the non-zero Y true. And then at the same time, we would like to identify the rank according to the index of the non-zero Y true value. And then you can see that we got these 1, 4, 2, 3. This is pretty simple because it's just like this is the 0 positions for the first rank. That let's give us a 1. And then the second one is 1, 2, 3. Sorry, the second one is 1, and then the third one is 2, and then the last one is 3. So that is 0, 1, 2, 3. This is 0, 1, 2, 3. Therefore, it will return me 1, 4, 2, 3. 1, 12, 2, 3 here. Finally, we can again assign a K value as a threshold to compare these vector and count how many ranks are higher than the K value and calculate their accuracy. Say for example, for K top equals to 1, so we count how many counts that are higher than or less than or equals to K top. So there's only 1, therefore 1 out of 4, we got 25% accuracy. And then for 2, because 2, we have these 2, they are less than or equals to K tops, K tops, which is 2, and in that case, 2 out of 5, we got 50% accuracy. And finally, we got the 75% because 3 out of 4 are predicted correctly. Now let's turn to the regressions metrics. The first one that I would like to talk about is the mean squared error. The mean squared error calculates the mean squared error between the true value and the predicted value. Let's take a look on this example. We have the Y true and Y predicts here. That is a 2 by 2 ND array, 1, 2, 1, 1, and then 3, 2, 1, 1. And let's run this cell first, and then we use, for this time, we just change it to mean square error and then update the state. Let's take a look on the result. Now the mean square error is equals to 1. Let's take a look on the calculations behind. First of all, we would like to calculate the squared error for each sample. In that case, we want to calculate the squared error for each sample before we take the average on the entire squared error sequence. Now, first, we calculate the squared error. And then once we have the squared error, we just take the mean as the second step. And then in that case, we just print out the value. Now again, by calculations, we can calculate that the mean square error is equals to 1. What about the mean absolute error? This very simple. This just calculate the mean absolute error between y true and y predict. Once again, we have the y true and y predict value exactly to the same as the two to the previous example. We got the same 2 by 2's ND away, but for this time, we just change it to mean absolute error. Now, let's take a look on the mean absolute error to see what kind of value that we have, that is 0.5. So first of all, we would like to calculate the absolute error for each sample. That is the absolute error between each of the sample, between the value y true and y predict. And then we take the mean, and that's it. We can calculate the mean absolute error. Finally, we have the mean absolute percentage error. It calculates the mean MAPE between the y true and y predict. Again, we have the same 2 by 2 matrix. For this time, we change this to mean absolute percentage error. We update the state to see how accurate we are. And then for the mean absolute percentage error, we got 50% correct. Now, let's take a look at the calculations behind. First of all, we calculate the absolute percentage error for each sample. So we calculate the absolute value, absolute error, and then divide it by the true value to get the absolute percentage error for each sample. And then we take the means for all of the samples. So we got the mean absolute percentage error. And let's take a look. We got 0.5, that is the 50% mean absolute percentage error. That's it for these videos. In the last 3 videos, we just went through all arguments in the compile functions. Once the model is ready and is compiled with specified loss functions, optimizers, and also optionally for some metrics, as well as the datasets are ready, fit functions can be used to fit the model with training data to start training. So in the next video, we will go through the fit functions in details. See you in the next video. Bye-bye.